more time?
We plan for now.
You plan, okay, that's good. Awesome. So the talk is about, as you can see, has the keywords defect, has the keyword exact, has the keyword correlators, it has the keyword Chern-Simons Matter theories. So this I know some of you guys are familiar with Chern-Simons Matter theories, correlators you know from CFT. Maybe defect is something that is less familiar if someone hasn't worked on this kind of objects. They have been around with us for a while, but I know not many of you not everyone is familiar with this type of objects. And exact just means exact in the coupling, in some coupling. So this was done with collaboration with a colleague of mine, Gunel Ferrando. He's in Beta Center in Bonn. There are two papers it's based on. One previous with my advisor and Gunel about these defects, and this is the recent one. So if you want to check, and this is my name, and now I'll talk about motivation. Before that, I have written notes, so if in the end someone wants, I can share them with them. They're like a summary of all this stuff compactly. So, okay, a bit of motivation for this work. So we're all familiar with the quantum field theory. It's a theory that unifies quantum mechanics and special relativity. We have a special type of QFTs, which are conformal field theories. This can be viewed as building blocks for QFTs. And we know that CFTs put strong constraints on correlators. For instance, we know that the 2-point function is fixed kinematically, the 3-point function, but the 4-point function is less fixed, and so on. And knowledge of the CFT data, which is the spectrum and the structure constants, suffices to determine via the OPE all the higher endpoints. So you can, in principle, write the 4 points as sums and so on. But it's very rare that you can actually compute this CFT data in D bigger than 2. So if you're in higher dimensional interacting CFT, it's very rare that you know all the spectrum and the structure constants.
Is there any example where we know it exactly?
Only in some sectors, I guess, right? In some particular cases, some limiting cases. So even in some, as I said, even in some solvable theories or some particular limiting cases, even then it's probably going to write it as some infinite sum over the CFT data, maybe in terms of conformal blocks and so on. So it's also beneficial to maybe attempt to, for instance, study these observables, higher endpoints, independently. Not as a sums, but directly work with them, with the observables. And to attack this problem in a general setup is very hard. So naively, what you do first thing is maybe use some limits, like large N limit, for instance. This will give you some control. But even then, when you do this, perturbation theory can be very challenging. You know, planar diagrams, keep track of that. It can be, even in solvable theories, it's very hard to do. One thing you can do is simplify your life by focusing on specific CFTs, which are the Chern-Simons Matter theories. They have this kind of properties which make them a bit more tractable. And in a sense, you can compute things there much more easily. And this will be today's talk setup. So this is this. I will review all of this, of course. My main object that I will be trying to get towards the end and show you the results about, it's always like that I have to give a very long introduction to accommodate you to the details, and only in the end I have like 5 minutes to show you the results. So the object is basically, you have something called a line defect, but it's not the infinite one like the Wilson line. It ends and starts on some operators that can be attached to this Wilson line. The Wilson line will be in the fundamental representation, will have two indices in the SUN, and it can attach to both ends with the operators in the fundamental representation. So each of them have one index. And so this is a gauge invariant object. So you can write something like this, and you can also ask what is the correlation functions of two of these guys when they are in the same axis. And yeah, this is the whole setup will be in what we call defect CFT defect conformal field theory is when you have a bulk CFT, but also you tune the line to be in the critical. I will review all of this. And essentially, we give this points insertion names. This is some operator. It's in some representation. And conformal field theory is not stronger as in the 3D because you want to preserve the line, so you have less symmetry. But still, you're able to fix this correlator up to one unknown function of 1 cross ratio. Chi is some kind of, if you want chi, some division between these points, if you're familiar with this type of stuff, and some kinematical prefactor, which captures the dimensions and so on of this stuff.
These lines are parallel and collinear?
Yeah, they're collinear. They're sitting, there's some space here, and they're collinear, yeah. That's the object I will try to, and the point is, in the large n limit, I can, in this setup, I can determine this function f completely for any Hooft coupling. I can do any operator you put here. I can find this function f. It's a very non-trivial statement. Not many examples you cannot find many examples like this. Yeah.
So x3, x2, these are the defects.
Yeah, those are what are called defect operators. Yeah.
What are these endpoints? Are they boundary of those defects?
Yeah, it's like yeah, good question. It's like phi dagger. I'm working with fermions, so let me use psi bar, psi bar, psi. Like they have spin, they have Lorentz spin, so 1 or 2. So it's going to be 2, maybe 2, stuff like this. It's like operators that sit at the endpoint. They have an index in the SUN, so they have some index, and it talks to the index of the Wilson line. That's how you make it gauge invariant. And in a particular, this is like in a particular realization using an action. But I can do it without an action also.
Yes. So suppose you worked in a gauge where A in the direction of the line is 0.
Yeah.
Then this is just a 4-point function of these fermions, right?
A 4-point function of these fermions?
Of these.
Ah, you mean when the... yeah, this doesn't contribute, you say?
Because that's 0.
Uh-huh.
They're 0. And these kind of quantities have been studied before in the context of scattering. I wonder if... we'll come back later. Let me show you this.
Yeah. Okay. And so yeah. So this is what I want to talk about. So
particularly, you can compute the spectrum of even the bulk.
So to get this, we will need the spectrum of the operators at these endpoints. We will use it as an input. It's something that you do before you, and then you input it as a yeah.
You're thinking of the closed bulk operators?
Bulk operators. So I thought you would get that from here.
But that is of course not. It's these single trace operators at large n.
At large.
So is the yeah?
Are the coordinates Euclidean, all the coordinates
Mm-hmm.
Euclidean?
I'm working with Euclidean signature. Yeah.
Okay, so
And the points are ordered. Yeah.
The first paper written on this.
Yeah, I'll review it. There is a Malda's board of paper. They did 3 points, you mean, all right.
Yeah, but the fact that the spectrum is known was clear.
I see.
Yeah.
Not in the function of lambda. Function of lambda.
It's not a function.
It is not.
For the single trace operators.
What was the question? What was
No,
that?
I'm just thinking that you have these two lines.
Yeah.
Right? And one way of doing that would be to do this OPE.
Yeah.
Right, and then you have a bunch of bulk operators.
It will be a sum of bulk operators.
Some bulk operators with some dimension.
Yeah.
Right, and then if you knew those, then presumably you can compute that.
Yeah, but it's again, it goes down to a sum.
Function and the 3-point function and so on. Yes, the sum is there.
You're going ahead already. Nice. So so what you're saying is that indeed you see this. Indeed, it's something that not many are familiar with, but these types of line, they can be essentially shrinked. You send this point to this point, and you can write them as a sum of local operators, double trace, single trace operators, double trace, and so on. Of course, with some 1/n. And indeed, you can write it as a sum, yeah.
At large, and you will just get.
Just at large n, this is just a sum of 2-point functions.
Two-point function of single trace operator.
Of single trace operators, we know them. You choose the normalization, whatever you want.
But then lambda dependence sits where? You just know the OP coefficient or not even there?
Yeah, the OP coefficient, yes, only in the OP coefficient, yeah. Yes, exactly. Because the single...
Computed earlier.
This is
No, these OP coefficients were computed here. No. No, Maldacena Zhiboyedov, they tell you about local operators, and here we're shrinking lines, so they didn't. But we did something analogous to them, and this compute for you this OP coefficient. This is here.
Good.
And you know them, then you can...
Yeah.
Exactly, but good.
This kind of problem could also be, asked and...
But a consistency in check should be that if I take 3 of these guys, indeed, if I project to a specific choice of,
then you get
then I should get it. If not, then it's a problem. But I should get it. I think because it's consistent. So, but good observation. And
this expansion coefficient is the same as finding a propagator in this gauge. Right, because in the gauge where this is 0,
the scalar expansion.
Yeah, so that in some sense.
So what are defects if someone is not familiar? I'll just give...
And another interesting thing is that this whole thing can be summed to get a nice function. That's another point, right?
Yeah, that's the amazing thing. I will get to what I mean by nice function. There's asterisks there, but potentially there is some work to do there. But that's, yeah. I'll show you this.
Cross-channel expansion then gives you new data?
Hmm?
The other cross-channel expansion gives you new data? The other expansion?
Where you shrink in the middle? Yeah, it gives you data on 3-point functions on the line. Yeah, which you should be able, it's something that is also a bit hard to compute sometimes, but it's also nice that you can extract from there. Yeah, good question. Wow, you're jumping ahead of me, and I like it. Okay, so what are defects? So if you're like a condensed matter theorist, you would think of you would start with some lattice of some points. Maybe you put here spin half, or you put some atoms, and you have a bunch of them here. And you would have some Hamiltonian that would capture the dynamics of the system. And defect would be adding here some H, they call it impurity sometime or whatever. It would be something like maybe acting with some magnetic field here, and this would be some kind of coupling a magnetic field to one of the degrees of freedom in a very local sense, really one lattice site or a few lattice sites. Or maybe you would do something else. You would maybe replace one of these points by a different atom. Maybe everything is like iron atoms, and this would be a gold atom or something. And then you would ask like new questions: what happens to the dynamics of the system, and so on. And so this is if you're like a high energy theorist, you would think of like typically replacing some region in space by new degrees of freedom, some line or some surface. So the most common thing we're all familiar with, like Wilson line. You take your space and you put some Wilson line in some direction, and this is really a defect. And we'll be concerned with this type of point of view, and the simplest one are line defects. And we'll be concerned with 3D theories, where it's 3D CFTs. So we'll tune the bulk. When I say bulk, I mean whatever is not on the line. We'll tune it to criticality. Like when every parameter in the action, you can imagine we choose them such that we have a 0 beta function away from the line. And then what we will do, we'll consider lines in this setup. And then these lines are still not necessarily, I'm jumping a bit ahead. So yeah, sorry, before I talk about the bulk, I want to say you should really think about this line operator, these line defects or line operators, they have many names, as really like embedding a one-dimensional quantum field theory in a higher dimensional quantum field theory. So they can have their own local dynamics, they can have their own RG flow and so on. You can really perturb them also and so on. And yeah, so the setup will be indeed 3D CFT. And we'll tune this like that, and then we'll ask the line to flow to some non-trivial fixed point. And we'll take the line. So yeah, so we'll take the so lines that are in their fixed points are called conformal lines. A line in RG fixed point. Their name is conformal line. Conformal line. And you can put them in any shape, kind of arbitrary shape you want, and they still preserve their conformality. But for simplicity, in order to have a bit symmetry, we'll place them to be stretched in the, like a straight path. And then we have, for a straight path, these types of lines, they preserve SL to R cross U1 in 3D. This U1 is because of the 3D. This is essentially the conformal group in one dimension. It has like 3 generators, translation in the direction of the line, special conformal transformation in the third direction, dilations. And this is like the rotation group around the line. In the transverse plane to the line. So
one question.
Yeah.
So in ordinary conformal field theory, one diagnostic of conformal invariance is that this trace of the stress tensor vanishes. What would be the corresponding statement for a defect being conformal?
Yeah, on a defect you don't have a stress tensor. There is no notion of that. You would have some, I mean, it's either if you have some, so a Wilson line, for instance, would be a candidate for a conformal line, and it comes with no coefficient because of gauge invariance. So, but you need to ask yourself: is there any, if you can perturb the Wilson line by some relevant deformation? And for instance, in the fermion sphere, you cannot find such a thing. So it will be your stable conformal line. There is no beta function for any coefficient there, for any. So yeah, so this will be
local characterization.
Local characterization.
We can talk about things being conformal defects, defects being conformal defects, kind of generally, right? Not just for Wilson lines. So I was wondering if there's a more universal characterization like we have in the bulk.
Yeah, in the sense like the stress tensor trace is 0, right? Nothing pops to mind right now, but I bet might be something there. Yeah, like yeah. Nothing pops to mind right now.
I mean, there are these displacement operators which are universal.
Yeah, they're like contact terms that appear on the, for the stress on the right-hand side of the divergence. Indeed, when you have this kind of defect, when you take the divergence of the stress tensor, you have here some contact term. And indeed, you have this appearance of this operator. You could say maybe the appearance of this operator, which is a protected operator of dimension 2 and spin 1, is a characteristic of these types of conformal line operators, indeed. It always happens that you have this.
Based on the defect, you still have scaling along the Wilson matrix. So
Yeah.
Yeah, this is what I wanted to get at.
so
I mean, how is it consistent to have bulk conformal symmetry, whatever you would observe by the line, but not the defect one? Is that what you're saying?
Yeah, I was thinking that something analogs to trace being 0 is that the projected trace is 0. I mean, you have to project the stress tensor along the direction in which.
Yeah, but it's not independently, I guess, conserved. So only the full thing is conserved, I guess. But But I agree that you can look at the specific components, and I guess that's what you're talking about, how it's related to measuring dimensions. Yeah, how you construct the dilations on the line. Yeah, yeah, that's true. But you only have this is the only thing you have, I want to say. You don't have anything extra.
Isn't it similar to boundaries? Like on the Wilson line, there is some additional condition. Like boundary system.
Additional what?
An additional equation. that you at the boundary. If you use Wilson line as a boundary.
In 2D maybe or something.
What kind of?
That I don't know.
The trace of the stress tensor, for instance, so presumably, does that have some contribution to the displacement operator?
Not that I'm aware of, no. I don't think so. No. But good question. I need to think about that. That's a good question.
Sorry.
Yeah.
Can we study this theory with the Wilson line as some perturbation on a theory without Wilson line? Adding a Wilson line is like adding some term in the Lagrangian, right?
Yeah, that's true. That's true. And then you can study correlation function in the presence of the Wilson line. Yeah.
So it's like doing some perturbation.
Yeah. Exactly. So when you introduce this kind of defects, and specifically the one that I'm talking about, there is some kind of new observables that you introduce. Basically now operators, they get expectation value in the presence of the line. So we call this the interplay between bulk and the line. Essentially now, if you have some local operator here, there is a 1-point function for it because you have the distance to the line, and this you can have also operator insertions on the line, which we call defect operators, as I said, and they have dimension. And because there is this SL2R, they have dimension and spin. And what this kind of correlation functions measure for you, they measure for you OP data. It's a new OP data type associated to the coefficients that appear when you try to expand the bulk operator in terms of defect operators. Up to now, is everything roughly okay? You're following? Any questions? Okay. Okay, so now I'll jump to discuss Chern-Simons Matter theories, and then we'll have all the necessary ingredients to move on.
Sorry, how
Yeah.
do you take OP of a local operator with a line defect? How do you take OP of a local operator with a line defect?
So you just expand it as, formally you just write some local operator, and you can write it as a sum of some defect operators on the line.
So if you have a line and there is a local operator here, you can surround the whole thing by a sphere. And then these lines would pierce the sphere.
Yes.
So the Hilbert space is not the standard one, but rather the decorated with 2 points. And then as you shrink it, the decoration stays, and then you get a point, and then that's like a point underneath it.
And the operators inside the sphere, is it different than the local operators that you have in the bulk?
Yeah, that's the boundary operator, O hat.
Okay.
Here it's like not necessarily the boundary operators. It will be this.
So not about defect operators.
Yeah, defect operators. Yeah. So yeah, the picture is something like this indeed. Yeah. So you have something like this, and you can replace this by a sum over with some specific operators running here. Let's say delta hat. The precise
mapping from O to O tilde is, can be worked out.
Yeah. This is exactly what computes for you some OP coefficients here are exactly these types of correlation functions. This lives on the line. So you compute this kind of correlation functions. You can by any method you want, either perturbation theory or some other method. And this is fixed by conformal symmetry up to a coefficient, up to several coefficients. And you can read from this coefficient that appear here. Yeah, that's the typical law for this stuff.
If you were working in the bosonic theory, the one without the Wilson-Fisher, then you'd have to do some tuning to make this Wilson line conformal?
Yeah.
And what is the nature of that tuning, just roughly?
Nature of the tuning?
It's some potential for phi on the line.
How does it look?
What do you actually do?
So if you're in the bosonic theory, you can write a Wilson line if you have a gauge, right? Let's write it down explicitly, right? So you can write the Wilson line. This is the bosonic theory, okay?
Oh, and then you come to phi as well to the line.
But then you look at the operators you have, and you see that you can write, because you're in 3 dimensions, the scalars have dimension half. So you can actually write something like some alpha over k, typically comes, and you have phi I, phi j, something like this. And indeed, when you're doing perturbation theory, you will see that this coupling runs, and you will find that it has, with normalization 2 pi, you find that it has 2 fixed points, alpha 1 and alpha minus 1. Oops. So what is the setup here? You go into Chern-Simons Matter theories using a microscopic realization using bosons. And you ask yourself, what are the type of conformal line operators I can have there? So naively, you start with the Wilson line, but then you will see that you also need to add this type of operator, which is like an adjoint. It has index I and index j. You could also have a singlet of this, but it will be suppressed in 1/n. And you will see when you do perturbation theory that this value, if you want it to be a conformal line operator such that you can discuss this DCFT stuff, there are only 2 values that it applies. This will be the stable, and this will be the unstable. And they have a bit of a different spectrum as well. Yeah.
And 0 is not a fixed point.
No, it's not a 0. No. Yeah.
So the bare Wilson line is sort of, if you make it bigger and bigger, you generate.
Yeah, you will have to generate this. Yeah, exactly. I'll actually comment about this type of operator. It's good that you ask. I will comment about this when we get to some applications of what I'm talking about. There is some new results I think is interesting. Right, so yeah, let me review Chern-Simons Matter theory. If someone is less familiar with these types of theories, I want you just to be accommodated to it. But I bet you probably all guys heard about Chern-Simons Matter theories from all directions.
Sorry, and if you take this operator with let's say one of these fixed points, and then you expand it in distance, would you still generate just the single trace operators or something now more?
You generate everything. I think you generate all of them, but we computed only the single trace coefficient, the coefficient of the single trace operator.
Leading order large n?
Yeah, it's single trace operators. Yeah, exactly. Yeah, excellent. Yeah, but you have, of course, to put here the boundary operators at the endpoints to make it gauge invariant. I mean, okay, you can also consider infinite line, but this won't generate.
So that naively that generates like double traces, triple traces, and so on, but those are suppressed in 1 over n. Bring those down. Because you get 5, 5, 5, 5, and so on. But those are all 1 over n suppressed. Is that right?
No, they contribute for you in the perturbation theory. They contribute.
So then you're not generating just single trace operators at leading order and larger.
Wait, I'm a bit confused.
Let's bring one factor down. Let's say you have the end operators, you bring one factor.
Yeah, let's do. Yeah.
No, he's doing Chern-Simons Matter theory, right?
You have this, right? You want to study this
Just like gauge field.
perturbation theory.
But that's why he has two files. Fundamental and fundamental.
Like that.
Yeah. So then this will hit that and that will hit that.
Right. So you will have a bunch of singlets.
Yeah.
Right.
So yeah, you're saying we start with something like this?
Like this, now bring down one factor of that.
Yeah, so you put it like this here. Indeed, to leading order, it will factorize.
Yeah.
I mean, but you, okay. What do I want to say to leading order?
But these contribute, you're saying.
Yeah. In perturbation theory, you indeed see them. I mean, they contribute, I want to say.
Yeah, okay, got it.
Um,
You get products of single trace operators.
yeah. Okay, so. So I'll just review shortly the Chern-Simons Matter theories. So how do we start? These are basically theories where you, from generality, you couple CS gauge fields, Chern-Simons gauge field, if you're familiar with, to either bosons or fermions in the fundamental matter. And there's a vast literature over this, huge literature over phases and dualities and so on. I'm going to focus on the phases where these theories are, you tune the parameters to be in the fixed point, so your beta function is 0. And there's 3D theories. And so we will consider these theories in the CFT and in the large N limit. Okay, so these are the, so if you want some kind of microscopic realization using fields, I will be working with some theory called the quasi-fermion. And a particular realization of it can be done using some kind of action of the form. So there we have some A, dA, so there's a trace. And this free interaction, and you'd have here, and you'd couple it to some kind of fermion, a massless fermion. So you'd have something like A plus D. I'm being schematic. If you want, I can be more precise about the indices and so on. But just to be so this is some action you can write down. Why is this a CFT? You can ask yourself what happens with the parameters here. So let's start with the fermion, for instance. You can write a kinetic term, then a mass term. But the mass term you can essentially tune to 0, and it will never be generated if you choose your specific regularization scheme. And then you don't have anything else that you can write. And this K, it's called the rank of the gauge of the rank, the level of the CS gauge, and it doesn't run. It's like a discrete number. And so essentially, it's an SU and CK. So there is an SUN gauge group here. So these are matrices. These are like vector columns. And we will study this theory in the limit that NC goes to infinity. And you keep N over K, NC over K to be fixed to some value. We call this the Hooft coupling. And it's a kind of a continuous number. And you can show that it runs between 1 and 1, minus 1 and 1.
Sorry,
Yeah.
Maybe irritating question that we
No.
can later. But,
No.
just going back to the bosonic theory.
Yeah.
Working in this gauge where I set A to 0 along the line, then we've got the propagator. I'm trying to understand what it means. So the statement.
Typically, we don't put, if you're thinking about light cone quantities, light cone, no,
No,
you
I'm
think,
thinking more like an A0 equals 0 gauge. Okay.
okay.
That's harder to work with, but has been done.
Yeah.
So we could look at your problem in that gauge, just conceptually. Okay. Now here it's just a propagator between these two guys.
Yeah, so you just draw it proper. Let's do it. Yeah, so it will be like that. You don't have the gauge. You're saying you set it to 0.
Now I'm trying to understand the statement that this the pure Wilson line. So it would have been just the propagator if we didn't have those phi's, right? The phi's change things. So I'm trying to understand that the statement that the pure Wilson line, is not RG stable. It's some statement about this propagator. I'm trying to understand what that statement is. Naively, it feels like the statement that the propagator is not scale invariant. But I thought that was not the case. So we can come back to this. I don't want to read it.
Yeah. I need to think about it because it's a bit.
It's different from how you think.
Yeah, exactly. I'm not used to setting the Wilson line in the direction.
Yeah.
But it's a good idea. I need to think about it. So this is the action you can write, and if you study this theory, you would find that you have the following spectrum in the large n limit. You have a dimension 2 scalar. We call it J0. You can realize it by psi bar psi, for instance, and then you have a tower of kind of currents that you can write down above it, starting with s equal 1 and so on. And they have dimension which is, so this is correct up to 1 over n. Let me just say this. And this is s plus 1 plus O1 over n. And they can be realized by writing something like a bilinear psi bar gamma mu. And then you have here a bunch of derivatives that you need to sprinkle in a symmetric traceless fashion. And this will be JS. A bunch of those guys along the way. And they will have this, if you study their 2-point function and so on, you will find that this is the dimension 2 leading order. And what's more special about this theory is that the divergence of S1 and S2 is completely conserved, but the divergence of the higher currents are broken by 1 over n effects. So this is S bigger than 2. This is a special thing for these types of vector theories. So generically, you won't have this. If you're like in n equal 4, for instance, where you have these currents, you can have them as well there. But there you will have here an O1 already. And this is very special for these types of theories, and people have done a lot of work on this stuff. And essentially one of the consequences of this is that, so first of all, if it's 0 here, this is like a free theory. It will tell you that it's a free theory. But if you have this type of stuff, it can be still powerful to use it to constrain, and I will review this in a second, yeah?
Just asking, S in super subscript is the number of derivatives that you will have sandwiched between the side by side.
Yeah. You need to make kind of to make it enough indices for it to be the S rank tensor you want it to be, and you write it in a fashion that is symmetric and traceless. Yeah.
Do you consider lambda type smaller than 1 because of Leverman theory? Because it's sufficient.
Lambda smaller than 1. Why is it bounded like this?
Yeah.
There is a story to it. Roughly speaking, there are two kind of.
Is it related to level rank duality? Or
Level rank duality.
That kappa is n plus k.
kappa is m plus k.
Okay, so take everything positive. So n divided by n plus k is between 1.
I see. So lambda is then nc over
K plus nc?
That's the like the
Kappa is NC plus.
Well, it depends on which regularization scheme you're dealing with.
Yeah.
But in one particular regularization scheme, a natural one, kappa is n plus k.
Yeah, there is you can regulate this theory by writing it in the UV using what we call a Young-Mills regularization. And there, this guy will get, you will call it K Young-Mills, and it will be corrected by N. And then you would ask that these two regularizations give the same observable, and you'd get this condition, essentially.
You know, the regulator, independent way of saying this is you can ask, what is the level of the Chern-Simons, of the Wessel-Witten theory, dual to the Chern-Simons theory?
Mm-hmm.
That is, some fixed thing.
Yeah.
If you call that K, then this kappa is n plus k.
Uh-huh. Yeah, and from there you can show that this has to be this kind of the values. And there are a lot, and I can also trace this condition to unitarity. Like you would see that you won't get meaningful things unless you live in this domain.
So here lambda is n over n plus k.
No, here lambda is n over k.
No, well, it depends on what your K is. If K is the level of the Wessel-Witten theory dual to the Chern-Simons, then lambda is n over n plus k.
K is there. But I think here just means the pair K.
No,
the level of the Lagrangian.
No, if you work in a dimensional regular, what the level of the Lagrangian is depends on what your regulator scheme is.
Yeah.
So dimensional regularization, you put kappa behind it there.
Yeah.
In the Yang-Mills regulator, you put k and they shift
Yeah.
it by n.
And yeah, exactly.
And so it's better not to talk about, because that's convention dependent. It's better to talk about something physical.
Yeah.
The physical quantity is what is the level of the Chern-Simons theory dual to, the Wessel-Witten theory dual to the Chern-Simons theory. Then that's a completely unambiguous statement. Okay, let's call that k.
Yeah.
Then lambda is equal to n over n plus k. With that definition.
Okay.
Okay, then it's
And then this,
convention independent.
Yeah. Okay.
Sorry, what is this weak coupling regime in lambda? Lambda close to 0?
A large coupling is close
Small
to
coupling.
small 0, yeah.
And large coupling is close to 1 or minus
1 or minus 1, yeah. And they're the same theory. They end up on the same point. Good. So yeah, if you want, so for instance, you can ask, the consequence, so I'm going back to this, so this is the spectrum of the single trace operators, and this is the divergence of the rank S tensor, and it's broken by 1 over n effects, and the consequence of the fact that it starts at 1 over n is the fact that these guys get anomalous dimension only at 1 over n. If you were in n equal 4, as I said, you would get here an O1, and it will translate immediately to the fact that these guys are not are already at the planar limit, get anomalous dimension. You can show it by studying the two-point function. And if you want a specific, how this specific form looks like, so in the large n limit, these are primaries, and you can use this fact to fix, for instance, their form on the right-hand side. So for instance, for d of the divergence of J3, you can show that it's 1 over n, and normal order double trace here would be something like J0, some derivative J1 schematically. It would be something like this. You can write it in a covariant form explicitly, and you use conformal symmetry to fix the right-hand side. And this is very powerful, because you can use it in word identities, like you use for the stress tensor. It can be still useful to apply to local observables, or what I'm going to talk about soon. And this is the main tool we'll be using. Because you see in the large n, you can use large n factorization, and you can factorize your correlators. I'm going to state a few properties of these theories. Then I'll review a bit of the lines in this we'll talk about the lines, and then I'll jump into specific details. Yeah.
So for this spectrum to follow, it is important that these fermions are in the fundamental of SUN or something.
Mm-hmm.
Is it important, or they can be in any?
Well, I'm not sure what happens if you choose a different representations for the fermions.
No, but it's very important.
Yeah.
If you choose adjoint, for instance, you know, the argument that the spectrum is unconnected is very simple. The argument is that this is a short representation. A short representation is a conformal.
Yeah, the condition that this is 0. Yeah.
Okay. Now, having a short representation of the conformal algebra, unlike supersymmetry, is generally not powerful, because the way it becomes long is short plus long gives long.
Yeah.
In conformal algebra, always. Supersymmetry has short plus short gives long. So if you control the short spectrum, you can say sometimes this pairing cannot happen. Okay, and you get indices. So conformal algebra, because short plus long gives long, and generally you have no control over the long, you generally can't say anything. But this is in the fundamental case, it's very special. It's very special because single trace operators mix with non-single trace operators only in some leading order.
Yeah.
So, and the single trace spectrum is just these J's. So you just look at the J's and you see there's nothing there available to pair up with this J to become long. Now suppose you had adjoints. Now your spectrum would be trace of blah 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 blah. The single trace operators would be trace of blah blah blah, would be Hagedorn growth. So it would be some huge spectrum. And you wouldn't have any control. So the key point here is that at large n, there is a closed algebra of single traces.
Exactly. Yes, exactly.
And that key uses key.
Yeah, exactly. If it were probably as a representation, you would probably can be able to write something here at leading order, and it will destroy.
Is there another complex representation?
What?
There is a complex representation of that code.
But you know, you'll have a CPT in your theory.
Yeah.
So if you have complex representation, you have a complex object.
Right. So the way fundamental comes with that.
Fundamental.
But you kind of pair it like that, right?
Yeah. Maybe if you have E8 or like, I don't know.
No, just curious, I mean.
Suppose you had 2 tensor.
Yeah.
2 tensor fundamental.
Exactly.
Now you'd be able to contract one index of the 2 tensor fundamental with one index of the 2 tensor anti-fundamental, and that would become an adjoint.
Right.
And which is important.
Yeah. Yeah.
So a few properties. As you can see, what's nice about this theories is the fact that the spectrum is of a free theory, right? Because this is simply the engineering dimensions to leading order. It's just the dimension you would read from the action. But still, if you study the 3-point functions, they're still non-trivial in the tooth coupling. The dependence on the tooth coupling is non-trivial. So it's somewhere between a free theory and interacting theory in that sense. And there's been works on that. In addition, people did in the past this Madasana-Zhibuyedov work in 2012. What they did is they said, okay, let's be agnostic to the specific microscopic realization. What they did is they bootstrapped. I would say what I mean by bootstrapped. They basically said, let's work directly with the 3-point functions, use the spectrum, use the conformal symmetry, use this thing of the divergence, which they call, it has a name by the name approximate higher spin symmetry, or slightly broken higher spin symmetry, because you have a control over how much you break the divergence in 1/n. And together with the Largent factorization, they were able to fix all the 3-point functions of all single trace operators in this theory as a function of 2 parameters, which they called lambda tilde and n tilde. These are just names that they are left over with, 2 parameters that are left after relating everything. And you can do a field theory computation and relate them to NC and lambda by some functions. So roughly speaking, they said we have this JS1, JS2, JS3, and they start with this observable. And now, once they set their observable, now they want to bootstrap it. They want to determine the right-hand side. So first, they're asking themselves, what conformal symmetry tells you about these correlators in this theory? And in conformal field theory in the dimension, this is fixed up to several coefficients. Actually, there are only 3 structures here. you can write it up to three coefficients. And after that, you have a lot of those now, right? Because depending on the choice, you have infinite family of these numbers. Now your question is, how do I reduce these numbers to just two parameters that kind of parameterize the space of these coefficients on the right-hand side? So what they do is they insert here this divergence. They use J4 because they were in some SON gauge group. They used only the even spins, but it can be generalized. And then what they did is they integrate this. And if it was just Jn here, like the stress tensor, this would be just, you would just use Gauss theorem and act with the charge on the constituents. But because this is not conserved in 1/n, there is a right-hand side as well. So the picture is that you have some charge acting on the correlator, on the constituents, JS1, JS2, JS3. But at the same time, you also need to integrate over the non-exactness on the right-hand side and use large n factorization. So it will be something like JS1, JS2, but then you'll have JS prime coming from the non-conservation and a two-point function, for instance, of JS3 with JS prime prime, for instance. So it has some schematic equations like this, a lot of them, sort of. And now you start relating the numbers. And it's, you can show that it's can be done. And eventually they fix these three-point functions. That's the technique, I mean, at the level of these equations. Any questions about this? Because I know it's a bit schematic, if you might miss the point here. But the point is that you use conformal symmetry to fix these correlators, and then you use the broken higher spin symmetry to relate a lot of numbers, eventually fixing these OP coefficients to be just a functions of two parameters.
How the higher spin currents are broken, is all the data known?
Yeah, exactly. To leading order in N, all the data is known.
Okay, so
exactly.
For all the high spin.
Yeah.
And then you relate using this switching between currents.
Yeah. The point is, but you don't have to know the coefficients. The point is that you don't have to know the coefficients. It's just an unknown parameter. In the end, it will be related among them, such that all the parameters are kind of related to each other, and there are two undetermined parameters. And there will be the Hooft coupling and the gauge rank. That's the name of the game. You start with many parameters. You place them whatever normalizations. You place them around. But in the end, you see that you have enough equations to relate all of them together.
And can you show why it will be just two?
It should be two because there's only two CFT parameters, which is N and Hooft coupling. You have nothing else.
But in the broken current equations, there are too many things, right?
Actually, no. It's kind of finite. It's you can only write here. A good question. You can only write here double traces and triple traces. This can be shown from dimension and spin and twist. So good. You don't have many parameters. It's an excellent question. There is a finite number of parameters here. And basically, we introduced maybe one or two here. And you just follow them up. And in the end, they kind of relate to whatever you have on the other side. Yeah, excellent question. Good.
But then there are too many equations then.
There are too many equations. Too many equations. You mean it could be somehow that the solution is zero or something?
Yes.
So apparently not. Apparently not. There is a unique solution that is not zero. Yeah, good question. Yeah.
If you were to do this in 4 dimensions, presumably you'd find only the free theories.
Yeah, exactly. Yeah, perhaps.
Only the free theories.
Actually, is it true?
I would imagine, because what is the deformation?
It could be something non-perturbative.
No, but you'd have to have a one parameter set. So it would have to then have a perturbation. If you want.
Mm-hmm.
I mean, or maybe there's something far away, but I'm saying the free theory will not be deformed into a line. Here, the free theory is being deformed into a line. Right?
Yes, exactly. Yeah. So yeah, but by this effect, it introduces like a family.
This has been shown. People have looked at this in this set of equation higher dimensions.
Yes, I think so. Yeah, there are papers by that. I'm not sure about how rigorous they were there, but I'm familiar with some papers. I think
Who are these papers?
they quote this. So I remember checking this out because I was curious about this in other theories. Because you see, it's very powerful. You can ask yourself, is it powerful in other places? But I think it's been checked. Maybe. Okay, you know what? No. Okay, I'll tell. Okay, I know what's been checked. Sorry, let me rephrase. I think when it's zero here, yeah. When it's not zero, I think it's very hard, probably. Because you have to determine what's appearing here, and probably if you have a very complicated spectrum, you can have a lot of stuff, and then you have less control. So
with this 1 over n squared term there, that is not determined up to a coefficient. Up to just a number, right? I mean the one not right. No. This triple trace, the triple trace one.
Yeah, it's determined up to a number.
It's just a number.
Yeah, it's a number. Yeah, because you know the spectrum of operators in the leading order, right? So you just write whatever you're allowed to write, and then you have some coefficient there.
But they don't depend on the spins of the things that appear.
There will
Many numbers.
many numbers. Even here, there will be many numbers, right? There will be.
Well, you were saying one number.
Finite.
No, but I mean, you take a high spin, there will be some.
Yeah. If you go to high enough, you'll have, yeah. But somehow it's enough to only choose one of them. Of course, you generate all of them, but it's enough to use only one of these guys in this kind of setup, and it's enough. And all the rest are probably consistency checks. Yeah. Good. So actually, it's good that you ask questions about this because I'll be using this kind of heavily later. Let me finish with the fact that these theories, they also admit line operators. So the Wilson line in these theories, as I said, this turns out to be a stable conformal line. And a stable conformal line operator, and you can study correlation functions in the presence of this line, of infinite line, but we will define something called a mesonic line operator. This is a line operator that has this boundary operators at the endpoint. So for instance, I can take psi bar W, psi 2, and this is also a gauge invariant operator, and I will study correlation functions of this and with local operators and maybe operator insertions on the line, but this will be the basic object I will be working on from here on. So this, for instance, sits at point x0, x1, this sits at point x0, and pictorially it looks something like this. You have these 2 points, and if you want, this is just a 2-point function on the line. From conformal symmetry, this is just a 2-point function. It can have a non-trivial normalization if you compute it in field theory, and I will talk about the operators in a second. And another name people like to give these operators, they like to call them defect creation operators and defect annihilation operators, because you see you start from the vacuum and suddenly you act with this operator and you create something, and this guy annihilates it, and then you go back to the vacuum. And you can also have operators on the line, for instance, and you'd call these operators defect-changing operators. The name defect-changing operator comes because you interpolate between one line and another line. And in some other theories, you can probably have 2 different lines here talking to each other via this operator in the middle. Just terminology. Okay, so now we can discuss these mesonic line operators.
The exact path that the Wilson line will take is irrelevant, right?
Again?
The exact shape of the Wilson line in this case is irrelevant, right? Only the 2 endpoints are the point.
Okay, so if you take a shape which is not a straight line, then you have less power because you don't preserve SL2R anymore, and the right-hand side will be a complicated function of the path. But if it's just a straight path, it will be just a two-point function times some normalization.
We have dynamical lambda here. It's not a logic. So the thing depends on it.
Yeah, it will depend heavily on the path. That's a great question. A great question. Okay, we're getting there. So from here on, I will be agnostic to a particular realization of the theory using fields, and agnostic to any dualities. You know, these theories, they have this theory of the quasi-fermion with the fermion. It has another description in terms of what people call critical boson, coupled to Chern-Simons, and it's like the strong coupling realization of these theories. I'll be agnostic to it. And I will also have, along the way, two parameters that will mimic tooth coupling and the gauge rank. And I will have a very large parameter, which is n, but it will be different from nc. I'll call it n, but it can be related to nc. And I will always take the line from here on to be stretched in the x3 direction as a straight line. Okay, so let me talk a bit about these mesonic line operators that are the basic object here. So you can have here this O bar. I call them O and O bar. This is the anti-fundamental operator. This is fundamental. As I said, this is just the fermion and some derivatives, right? So people studied the spectrum of these operators, how they look like. So already in the planar limit, they receive anomalous dimension. So it's engineering dimension plus some function of the Hooft coupling plus 1 over n. So already they have anomalous dimension. They are classified by two quantum numbers. So because it's preserved SL2R, they have here the dimension, which is the positive non-negative number, and some spin, which can be fractional. So how does the spectrum look like? So let me maybe write it otherwise. So yeah. So you have here O. So you can have here, let's say, half, and this will be a dimension. So this is dimension delta. I will say what delta is in a second. And the tree-level spin is half. And then you can have on top of it another operator. I call it O bar 3 over 2, and it has dimension delta plus 1. And above it, there is another operator, 5 over 2, dimension delta plus 1, and go on until infinity. Below, this is one tower.
Sorry, spin means quantum number under this U1 rotation?
Yeah, exactly. It's under the U1 rotation group. And below it, there is another operator, minus half. And it has dimension 2 minus delta. And below it, 3 over 2 bar has dimension 3 delta.
So how are we talking about deltas of non-gauge invariant operators?
Delta is a parameter here. A parameter. It's the dimension of this operator. It's just a name. It's not, don't confuse it with the quantum number delta. It's just it's a very bad choice for the dimension of an operator in this spectrum. And
delta is not the how O is charged under the D of the full.
Yeah, delta is exactly this. This is the dimension of the operators.
So it's delta is exactly D of the full 3D theory on this will give you.
No, it's the SL2R. The dilatation.
No, but dilatation on this line or like the full D?
I guess the 3D.
The 3D.
I guess the 3D, yeah.
So you would have to look at the sphere with one decoration and then shrink it.
One decoration, then shrink it.
Transformation properties, because it's an endpoint, right?
Again?
So this operator is an endpoint of the line.
Yeah.
So you can put it at the origin and let the line go off to infinity.
Okay.
And then you look at the sphere around it. So that sphere will then be pierced by a single line. the vertical point, and then you can look at the transformation properties of that state.
Mm-hmm.
Is that what that delta means?
It's just the scaling dimension of the operator.
I mean, usually we talk about gauge invariant things, right?
Yeah, this is a gauge invariant object.
Not O, right? O is not
On itself, it's not a gauge invariant object.
We are
That's-
still talking about its dimension. That's what I'm asking.
Mm-hmm. I see.
Could you just ask how the expectation value of this thing scales as a function of?
Yeah, exactly. This is what I think I'm doing. Yeah.
Some tight line between.
Yeah, so this is the line, and you look at how the expectation value of this scales as a function of how big the line is. That defines.
Yeah. I think this is the way it's done. Yeah.
Yeah. Assuming the line is tight, right?
Straight.
Yeah, exactly.
That should be power law.
Well, that should be power law. And you take that scaling, and half of that scaling is the dimension.
Yeah.
Why should that be power law?
Why should that be power law? Because everything is conformal, right?
No, but this line has something.
Some length. So you take this whole thing, you take the whole space-time, and you do a binary scaling on it. That should give you back, some power of the white. Just take a photograph and blow it up. Should be scaling there.
But how is it different than if you don't have any
Yeah,
thing
that's
in
right.
between?
If you didn't have anything in the middle, you'd have the vacuum. So it's not changing.
That's yeah, exactly.
Here you get some number, some answer for this expectation value. You blow it up, the answer changes. But as a function of this distance, right? The power law. It's like a 2-point function.
Yeah, and then exactly you ask how by how much it changes, and this is how you read off the dimension.
In fact, in a particular, yeah.
Yeah. Okay, and so on the right and on the left we have two towers. This is 2 minus delta with spin half, and here 3/2 with delta plus 1, and so on. And these are the possible operators in the spectrum. And U1 forces you to always pick them to have the sum of the spins to be 0. And yeah, just memorize this, I guess. And apparently, if you do a field theory computation, this delta is just 1 plus lambda over 2. So it only gets one loop correction in the dimension. And also, you can show that the spins of these operators at the endpoints, they also get anomalous dimension. And this has to do with this framing and bosonization in these theories. But I won't go into this. Yeah, so this is roughly...
Delta is 1. Where was the 1 place at point? You had half. So I'm getting this up to. Without the lambda by 2, where did you write the 1 before?
One is this
It's
is
2 of them together. Yeah, got it.
2 of them together.
It's the half and half, right?
Yeah. This is the expectation value, and this is one operator. But the dimension of this guy is 1 plus lambda over 2.
So then I mentioned the full composite.
So, for instance, a mesonic line operator. So, for instance, you can write something like this, like you.
Just the single guy.
Single guy.
Are you talking about the single guy, the delta?
Delta is for a single guy, yeah.
Oh, because it's a fermion.
It's a fermion, yeah.
Fermion. So delta is 1 in 3.
Yeah. So you can write something, you can write an expectation value of the form. So specifically it will look like O bar at 1, half, WO minus half. And this is just some normalization divided by, just from the 2-point function.
Yeah, got it. And sorry, and what was this 2 minus delta? Sorry.
It's an operator in the spectrum with dimension 2 minus delta. You can have such an operator.
And when you went, sorry, I'm just getting confused. So delta minus 1 is...
Yeah, let me write maybe the field theory realization. So this is like psi 2. This is d plus psi 2, and so on. And this is psi 1. This is psi 1. This is like a 3-level realization. And the metric is... ds 2 dx plus dx minus plus dx free.
And that was delta, delta minus 1. What was the next one? Delta plus 1.
Yeah, they're all integer integer one spaced.
Okay, fine.
Is it delta plus 1, delta plus 2?
That's
Yeah.
correct. Yeah.
Yeah, this is plus 2.
Oh, there was no minus. That was what was confusing.
Sorry. It's all going up.
Okay, got it.
Yeah.
Got it.
And so yeah, you can easily remember the spectrum. It's very simple.
And why is there this other tower gets delta 2 minus delta and so on?
Why does it get it like that?
Rather than delta, I don't know, whatever why is that the natural thing?
You're asking from a symmetry perspective or something.
Like
Technically, this is what you get. Technically.
as a function of lambda, you're saying, right? So yeah, I guess it should be determined by some conformal symmetry. There's a multiplet. I mean, the tower there I can understand. That's the multiplet. So that's some conform multiplet, right? Starting with some base lambda.
No, it's not a multiplet. They're all primaries. They're independent.
Primaries with respect to what? Clearly, it's a multiplet with respect to the bigger one, right?
No. You're on the line. This is not a descendant.
Yeah. That's fine. I mean, the line there will not be.
Yeah.
But I'm saying it from a global point of view.
Derivatives of the fermion are descendants of the fermion, roughly. Is what he's saying.
That's what I'm saying. So that I can understand. I don't understand this thing.
The bottom one.
Minus delta. Why there's a minus sign for delta?
I can tell you why. If it wasn't, I would be in a problem.
So is it this Casimir is invariant under delta goes to 1 minus delta?
But this is no. This is you mean the shadow or something? I don't think this is the case. No, I don't think. No. I don't have right now an intuition. I will tell you this. If you didn't have this, guys, you wouldn't be able to define the displacement operator. Because the displacement operator is a dimension 2 operator with spin -1 or +1. And you can see that only a combination of these two on the middle of the line can create such an operator. So it must exist, sort of. Why technically, technically you can show it, and this is maybe a reason why you must have it.
I see. And when we take the thing of the full guy, do the lambdas cancel out?
So this delta, it can appear here in the power. It will appear in the power here. But you can define operators in the middle of the line, these defect-changing operators. And for instance, in the leading order, it's just O times O bar. You can really think them of adjoint operators. And their dimensions are just the dimensions of the constituents, and the spin is just the sum of the constituents. So you see, the only candidate to get a displacement operator is to take delta and 2 minus delta, for instance, together, to take these two operators, and this will be O minus half times O bar minus half. And this will be your displacement operator on this line.
So if bars are on this side, the other bars are on that side, right?
Yeah, but is that so you have to, so you have O bar O, O bar O, right? So you have to have it like that. You see, it's O bar O, so you have to have.
So that combines with that. Right?
Yeah. So the two leading order, they factorize indeed. Yeah.
This is confusing. You're saying that this composite operator scales not like dimension 2. It's not. That's different from the propagator, which is what's confusing. But I lost it.
Okay, the displacement operator at least I can understand, because that's a spin half has to go with spin half to make a spin 1, which is a vector.
Yeah.
But the way you are drawn the line, that's a scalar in the transverse rotation, because spin half with minus half. So that need not.
All the representations are just U1 or what?
Yeah, this U1.
Yeah. So just the representations are just defined by numbers.
Yeah. Right. So I'm just saying that the displacement operator, the fact that it is 1,
Yeah.
can tell you that that should be delta there and 2 minus delta there.
Yeah. That must. Yeah, if you define one of them to be delta, the other one must be 2 minus delta. You parameterize this to be delta, then you find it in field theory is just 1 plus lambda over 2, and then this must be 2 minus delta. Yeah.
The lambda over 2 is the same as the renormalization of the spin, right?
Yeah,
Including the
yeah, because the thing is you can, I'm not sure about the details, but the thing is you can lift these types of operators into a supersymmetric setup. And there you have this BPS condition where the spin and the dimension must be kind of equated. That's why they have kind of roughly the same anomalous dimension. Okay,
Sorry,
yeah.
Why the spin negative spin operators coming? That would make the theory non-unitary, right?
No, spin can be negative. It's just a number. The dimension
No,
cannot be
spin
negative.
minus half representation, right? That operator is in spin minus half representation.
Of the U1, it's okay. I mean, there's no problem with having negative spin. It's just rotation in the other direction.
No, is it the J3? Is it how that operator is charged under the J3 or the full J?
J.
Just the J3,
Just the J3. Okay.
But the only thing, indeed, from a unitarity perspective, this delta must be positive. If you're concerned about this must be positive. This was okay. By the way, you can see from here that you also have to demand this to be positive, right? And delta can only be between 0 and 2, for instance. Let me jump now to results of our previous paper. So now that you have a picture of these lines, you see, very, very cool lines, let's talk about how they talk with the bulk, okay? So let me ask you this, tell you about this. So now I'm considering the following setup. I want to understand how these types of line talk with the bulk. This would be the most natural observable is just to take a bulk operator, these currents, in the presence of these lines. So we take this, we put here some bulk operator JS feed, let's call it, and then I have O bar S, that's S1, O bar S. And I ask what is the correlation function of this object? What is on the right-hand side? And apparently, conformal symmetry is not enough to fix this configuration. Even though you have SL2R cross UI, it's not enough. A simple just counting of degrees of freedom. This is position, has one position. This has 3 positions, like a 3-dimensional position. So 5 degrees of freedom. But SL2R cross U1 is just 4 generators. So you're stuck with one unknown function. And apparently this function is exactly the angle here. So at the end of the day, this whole thing is just some kinematical prefactor times some function of the cosine of the angle. And so what we did in this paper, we set out to study these functions and see if we can do something similar to Maldacena-Gibouedov from 2012. This paper I told you about that fixed all the 3-point functions of local single trace operators in terms of these 2 parameters. Apparently, this looks very similar, right? It's a 3-point function. Okay, it's not 3 local operators. Now it's 1 local operator with a line, but it looks like a 3-point function, but it's not fixed by conformal symmetry. So first thing we did is find these functions. To do it, we used translation transverse to the direction of the line. It's not a symmetry that preserves this configuration, but we know how it acts on the constituents. This allowed us to find these functions. And then we used the Maldacena-Gibouedov technique where we inserted the divergence of a current and then used it to relate all these coefficients. I'm being
in the bulk.
Also on the line. It also acts on the line. Or what?
So the current is a bulk.
Yeah, the current is a bulk operator. So
the information about the position of the JS tilde will be in the kinematic part.
Yes. But also, roughly speaking here,
then there's also this, you can have many theta many different positions corresponding to the same theta.
Yes.
So kinematic will help you fix the position dependence.
The kinematic will help.
That has been done. So the distillation is that it should be only function of cos theta. That's your dynamics.
Can you explain the question?
No, I was saying in the kinematic you will have all the information about.
Yeah, the positions will be there. The positions will be there. Yeah, exactly. I will show an example in a second. But roughly speaking, this correlation functions, they look something like this. O bar W, O bar. This is position x1, x0. They have spin 1, spin 0, and there is some JS here at position x2. And so first we act with first you act with the generator of translations, transverse to the line. So this is just P plus minus. We use that. This gives you f of cosine theta. Essentially, it gives you several differential equations which determine f of cosine theta. F of cosine theta is a function of, it depends on the representations here. And we do this for any mesonic line.
Sorry, I mean, just tell me this is the current there, right? So,
Yeah.
minus energy, though, they would insert this, the word identity, right?
So in addition, there will be another divergence.
And then you do some weak contractions.
Weak contractions. Not sure about that.
You would compute that in the free theory, right?
No.
No, sorry, then sorry.
I'll explain. So first, we fix this. We fix this using conformal symmetry.
Yeah.
This is this.
Yeah.
Then we choose. We fix this. We look at specific bulk operator here, and for any line, we use translation in transverse direction to the line, and this gives you f of cosine theta. So for any mesonic line with fixed bulk operator, we can determine all of these correlation functions up to one number. So apparently, if you study for a fixed bulk operator, you can determine this, all of them up to one number. Now you have many of them. For each choice of J0, it comes with a different number for any mesonic line. Now you have many numbers.
You determine this f from this kind of analysis.
Yeah, you just act with the translation generator. You know how it acts on the constituents here, and you find a differential equation, and you solve for it, roughly speaking. I can...
just conformal symmetry will not give you f of
No.
theta. So
No.
what is the other symmetry that is being used here?
It's not it's like you use the translation generator in the transverse direction. It doesn't preserve it changes the configuration, right? Because it moves you to a different type.
But it's still part of some higher dimensional conformal symmetry.
Yeah, it's of the 3D, of course.
Yeah.
It's of the 3D group.
Even that will not give you anything, right?
But this will fix this function f. Apparently, it fixes you the function f.
I think he's not translating both. He's only keeping this fixed and translating this.
Okay.
No, I'm translating everything.
But then that does nothing, right?
But I know how it acts on the constituents. Roughly speaking, and I'll show you how it works. So, for instance, let's take this line, for instance. I'll show you how technically it's done with some, let's say, scalar operator. And now I act with translation on all of this in the plus transverse direction. So what does it give me? So I act on each thing separately. So when it acts on the first one, it will create an operator. So what is this? What is P plus O bar half? This is the dimension delta and spin half. So what can it give me? It can give me an operator of dimension, it can give me the dimension operator of dimension delta plus and spin 3/2. But this is exactly O bar 3/2. There's nothing else that can be. So that's how I know how it acts on them. Kind of, I know how they transform covariantly under the generator. Sort of. And I act on the constituents, and I get some differential equation. You see, because it kind of relates between different. it relates between these types of different correlators, but with different boundary operators, but with the same bulk operator. Because on the bulk operator, P plus just acts as infinitesimal derivative. Yeah. So this is just D plus J0, right? But on the boundary operator, it just moves them along the tower.
Okay, but then you relate this in one operator to that in some other operator. But how do you close the system?
Excellent. So for a given bulk operator and any line, when I say any line, I mean any boundary operators on the line, I use this P plus P minus, and I relate all of them together to one number in the end of the day.
One function, right?
One number. This function is determined, actually.
Why? How is that determined?
So when you do this process of acting, you get a bunch of correlators in a linear in an equation, sort of, and you have kind of several functions, and you have several equations, and then you just solve for them, and that determines you these functions.
You write down
a system of differential equations. So you would have. So you see, you have.
That's triangular, right? I mean, you're not coming back. So if P plus hits that, you get higher thing.
That's true.
Keep on
So
getting higher things. So it will just, the ignorance will propagate on this side. How do you come back and close it?
no, it's closed actually for okay. So it's closed in the sense that all of them can be related up to one number that I cannot fix.
But why not one function? It seems to me that you're not changing theta when you do this, because if you're moving everything, you're keeping theta fixed. So you're not relating one theta to another theta. So how do you get the functions?
So I'll show you how it's technically done, and maybe this will be more clear. Yeah, so this example is okay, I guess. Roughly speaking, when you act with translation generator, you get on the right-hand side, you get, for instance, O bar 3 over 2, W O half, J0, plus O half bar W 3 over 2, and you get O bar half W O half J0 with a D plus, for instance. And this is equal to 0.
What about the W?
Yeah, so at this specific configuration, the displacement doesn't contribute. So when P plus hits W, it creates a displacement operator because it's like you're deforming the line a bit in the translator direction. This is similar to inserting a displacement operator, but it factorizes and it's 0. So it doesn't contribute. Anyway, the point is that this is the only relevant contribution. So you see you have a correlator here. Each one of them comes with a different function f, and they just relate among themselves. And you can just do it schematically for any S and S bar, and it's just can be fixed up to one number.
You have that half-half kind of thing, right? But now I have 3/2, 3/2. So now how do I make that? How do I compute those?
So then you take a generic spins, and you act with this, and it gives you some kind of recursion relation between all them.
You just go ahead, right? Keep on going ahead. So
yeah, but all of them are related up to one number in the end. You can show that it's just. Yeah, you do it kind of.
For example, now if you want to do 3/2, 3/2, you can write down a similar equation for that. You will get 5/2.
Yeah, but all of them are in the end related to each other. You can all of them in the end appear in all of the equations, and you can relate them all together.
Yeah, well, that is what I don't see.
Well, it's a technical step, but it's possible. I mean, yeah, you want.
Strong statement, right? You're saying the symmetry is able to fix this thing. I just want to see how symmetry can fix this function. Usual conformal field theory is if you have a piece of a defect, conformal defect, and a local operator, you agree that it will not be fixed, right?
Yeah, that's the case. It's indeed not fixed. Because I'm not using conformal symmetry here only, right? It's not only conformal symmetry here.
Yes.
Because I'm using the knowledge of the spectrum.
Okay.
So for a generic theory, you won't be able to do it. That's the problem. For a generic theory, you don't know what is P plus of O bar half. It can be something very different. Here I know the spectrum of the boundary operator, so I just input it as an information. Right? This is the ingredient. Maybe I wasn't.
I still don't see it, even with that.
Well, but then you see you have some function here, some function here, some function here. You have 3 equations. You can show that you have 3 equations. they relate them among themselves, and then you can go on and so on, and in the end you can show that everything is related to just one number. Yeah, it's kind of technical. I can show you later, I mean, more details, like how you practically do it. But the point is that it's possible to do it.
There's also P minus equation.
Yeah. You can use P plus, P minus. You have several equations.
But then there will be different operators. That will be
Yeah.
3.5.
Some of them are useful, some of them are not useful. The point is that in the end, you can relate all of them for a given bulk operator to one number. But now, for any given bulk operator, you have a number that is not related. So is a number. Now you want to relate among themselves all of those numbers. And this is where you use this Madasena-Zhibouedov technique, where you consider, now after you determined for a given bulk operator and any mesonic line operator, you determine it up to a number where this function is now known explicitly. Now you take this correlator, okay, here, and you insert here the divergence of the J free current, and you integrate over it. And now, from one hand, you use Gauss theorem, where you have this acting with the charges on the constituents, and you know how it acts. And on the other hand, you need to integrate over the non-exactness of this. And it's also a closed system. And in the end, after we do this, exactly like Madasena-Zhibouedov did, you get that all of these coefficients are related among themselves, and we cannot fix two. One of them is going to be the Hooft coupling, analogous of the Hooft coupling, and one of them is going to be a large n parameter that appears in this kind of thing. And that's the name of the game. So in the end, we get something consistent, and we're able to also fix these functions. But I want to emphasize the fact that we can fix this function is only possible because we know the spectrum. So if you don't know the spectrum, it will not be possible, probably. So what kind of dynamical information you have here? This is very nice. So from one point, you can, there are two OP limits for this.
Just in Madasena,
Yeah.
so when you look at this, when you substitute this JJ quadratic piece there.
Yeah, let me show it explicitly.
You just compute it in the free theory, right?
No, everything is in the interacting. So you get, when you do this, you get the action of the charge on the constituents.
You large n factorize.
And then you use large n factorization where
That's like free theory, right?
But it's relating it to 3-point function, 2-point function in the interactive thing.
Yes.
But you get a closed system. You get a closed system for
yeah,
any point of.
so something something like this, roughly speaking. And then you get a closed system, and all of the coefficients get related, and you cannot fix the, and again, the same thing.
Okay, yes.
So what kind of information does this correlator contains? It contains two OP coefficients types. One is when I send this operator to the line. This is the limit where I'm shrinking this mesonic line, and I can write it as a sum of single trace local operators. This is this limit when I send it to here. This is the coefficients that will appear here. Another limit is if I send the bulk operator to the line, and this would be the limit where I'm expanding this bulk operator in terms of local operators. So it contains two distinct OP limits. And yeah, that's roughly what I wanted to tell you about this. And now we can jump into, do you want me to show you examples of these functions? How they look like, these functions? Would you like to see? Yeah. So for instance, if you do this, so the simplest one is the bulk, if you do it with the bulk scalar. Because the higher representations you have, the more you can have several functions of this of 1-cross ratio. So the higher you go, essentially it goes like 2s plus 1. You can have 2s plus 1 functions a priori. But all of them are then can be fixed to be one number, up to one number. So for instance, if I take O bar half W, O half, with J0. So this is some number. I call this types of hypergeometric. 2, 1 minus 2 delta, 2 minus delta, and then 1 minus cosine theta over 2 divided by x10, 2 delta minus 2, x21. So you get hypergeometric, but, so this is dimension delta, dimension 2, and this is what you find. So you really find the explicit function here. But if you take O bar half, O half, J0, so I just take delta here and 2 minus delta here, and dimension 2. Now this is just, this is x1, so this is x2 minus f half over minus 1 to delta plus 1 by 2 delta.
Oh,
There is no, the function here is just a number.
oh, could it be that it's just a conformal block?
It's not. It's not. But you can expand it in conformal block of SL to R.
Meaning what I mean is that if you do the OPE of OS bar, the guy that runs and meets the JS is JS itself. Or no? Yeah.
I just want to emphasize that this is not a conformal block, but you can expand this in conformal blocks. You can do this, but it's not a conformal block of a primary in the bulk or something like that, or some primary in the SL2R.
Yeah, it will have to be, right? You're saying that the OP of O bar, if you make that a bulk operator,
Yeah.
that will have to be yes.
Ye-
It has to be.
So that will fix the function completely. Usually the infinity of the sum translates into dependence of things, right? Dependence on cross ratios. This is some fake dependence. It doesn't really exist because there's only one guy that meets. So it's just a conformal block of that guy roughly.
You say when you.
Yes, the distance is just how it falls out. That's absolutely fine.
So you're saying because you shrink it, there's only one.
Yeah, one guy goes there and meets JS. So it's even though it kind of looks like it's.
No, but it's not exactly. No. There's not only one guy. Remember, we have SL2R.
Multiplet, let's say.
You have SL2R, so.
No, what he's doing is expanding in bulk operators.
So you want to use 3D conformal block or something?
Yeah.
Okay, probably then, yeah. Then from the 3D perspective, there's only one.
He's saying that it looks like 4-point function, but it is a 3-point function.
Yeah, exactly. But from the SL2R perspective, there are infinite operators, right? Because you can have now D plus D minus acting on these operators. It's a primary as well.
You kind of collapse this and make a bulk operator and go meet that guy.
Yeah. From a 3D perspective, I agree. It's only one primary.
One primary. So
Yeah. Yeah, that's true.
It looks like a conformal block as it should. I mean, maybe you're saying it's not, but maybe it's somewhat related.
Yeah. You're saying all you need is what it becomes in the middle.
Yeah.
And once you have that, you have everything.
You have everything.
Got it.
All right, good. Any questions about that? Because now I'm going to go into the recent paper results. This is like the previous results, and now I'm going to, essentially we determined all of these functions. We know explicitly, we know most of those dependents. Obviously, the more higher you go in representations, it becomes super complicated. Like the differential equations are hell, but essentially we have a technique to solve all of them. It's just a matter of computation power. Yeah.
Just a small question. How do we know that we have all the information about the spectrum of the theory?
Well, you computed it.
No, but how do we know that? How do we know that there isn't more than the spectrum that you written?
So there are two ways you can verify this. One, you could go to a specific macroscopic realization.
Of this Chern-Simons?
Yeah, and then you just, you write what you can and you find what you can. Another way you can do is by bootstrapping this spectrum, by stating the axioms of Chern-Simons Matter, which align with the Chern-Simons Matter theories. You write some axioms that are very general and they align with it. and you try not to be too harsh on yourself, and then you see that this is the only spectrum that is, you find a unique spectrum. You can you parameterize the spectrum by this delta, and you find that this is the only thing that is consistent with the axioms you put. So there are two different ways to show it, but and it's consistent. Yeah, but it's a good question. Yeah. All right. So now I want to share a bit of recent results, which are interesting in my mind. We're almost over, guys. Okay. So one thing you can do with this correlators of a line with the bulk operator is you can use them to find, so remember these boundary operators? They go like delta plus some number, right? And they have like a 1 over n. So one thing you can do is determine this 1 over n here using the correlators I just talked about. How it's done? It's technical, but the idea is that you can write some equation. You can write an equation which you can write something like m with j2 and some kind of a word identity for these mesonic correlators and study it in 1 over n. And eventually it tells you that essentially it gives you an equation for the relative dimension between the boundary operators. So how I'll do it? Let me see. So let's define like that. Let's look at O bar half. Its dimension O bar 3 over 2, O bar 5 over 2. So remember, this has dimension delta. This has dimension delta plus 1. This has dimension delta plus 2. And even above them, we have also O bar 7 over 2, delta plus 3. Oops. But this is O1. This is like leading order. At subleading order, let's define the distance here to call it delta gamma minus half. This distance to define it delta gamma 3 over 2. And this distance to define delta gamma minus 5 over 2. And this is like the order O1 over n. So our techniques, now that I will roughly say, is that we can determine only the relative coefficients between these boundary operators at 1 over n. And we cannot do better. This is because one of our parameters in the theory is this delta. This is like associated to the Hooft limit, as I showed you before. And it's the exact dimension of the operator O bar half. And so we cannot, it's a parameter in the theory, we cannot fix it. So
can't you fix it relative to what the bulk 3-point functions are, for instance?
Probably.
Because that already defines.
I can relate it to the anomalous dimension.
Correct.
Yeah, it can be done, but it's quite.
It's hard, right?
Yeah, it's a bit annoying to do, but it can be done indeed. Yeah. But the point, we have access only to this relative anomalous dimension if we're using this parameterization. And essentially, if you want, you need to tell me what is delta in field theory, and I can tell you what are the towers, what is the spectrum of the tower of operators above it to order 1 over n. Essentially, to do it, we use, let me be schematic, we use word identity. For the mesonic lines. And then we find the following equation. Delta gamma S is CS over CS minus 1 with 1 over n here, where S is negative. And what is CS? CS is the 3-point function O bar 1 minus S D minus W OS, and CS is M minus S S. So this is a 3-point function, on the line. So it has a boundary operator and a displacement in the middle. And this is just O minus S OS. So this is the equation that you can derive from some word identity that determines this relative dimension. This is the most we can do in the setup because we chose, again, this to be a parameter in the theory. It's not fixed. And these guys can be computed using the bulk line correlators I told you about. We can access them directly using the correlators I showed you. So in this sense, this is an application of what we did. I want to share with you a picture now of how I plot this function now. Delta runs between half and 3/2. And I want to show you now a graph. I will plot it physically. And I will show you how it looks like. I think I'll remove this because this is an equation. It's not very interesting. I want to plot you this, and this is physics, okay?
So this delta was coefficient of the 1 over n correction.
Yeah, this is like so delta gamma minus half is the this dimension minus this dimension at 1 over n.
1 over n. And what you're going to plot is that.
I'm going to plot these guys now.
Okay.
Yeah. As delta, as a function of delta. Where delta is like the Hooft coupling. Lambda, yeah. I just plot it as a function of lambda in some sense. So, yeah, let me show you how it looks like. This is a very cool plot. So, okay, so how do I do it? So this is delta. This would be n delta gamma. So let's do one color where, so let's do, this will be delta equal 1. This would be delta 3/2. And this would be, let's see.
Sorry, just 1 second. Maybe I missed. So you had this, finally in the previous code, you had this function, and then you had determined this 3-point function, right?
Yeah, I have them all known explicitly up to n and delta. Which is delta is a Hooft coupling, if you want.
And from there, how are you computing these consecutive differences?
So this delta gammas, I can find an equation using some word identity, which says that delta gamma is Cs over C, where Cs is just a 3-point function on a line, and Cs is essentially, yes, minus 1, I think, is a normalization of, it's just a 2-point function of the mesonic line. It's a mesonic line expectation value. And essentially these guys, I can compute them using these bulk line correlators. There is some equation that determines them. So I don't know if this is known. I think it's known, this formula, in other theories. Essentially, kind of, if you have correlators with displacement, it somehow it contains the information about the anomalous dimension.
I see. Yeah.
I think it's something known in the literature. Like we found it independent. We didn't know about this. We found it independently. But apparently, after we looked, we thought about this. Maybe it can be more general, but it's something known. So how does this plot look like? So it starts its life something like this, and then it goes like this, and this guy then, and the line. Finally, we have. So this is delta gamma 5/2. This is delta gamma 3/2, and this is delta half.
Sorry, and can you translate your capital delta to lambda?
Yeah, let me write it explicitly, just for the. So
Sorry.
yeah.
Lambda and minus lambda are kind of equal. equivalent?
Yeah.
So shouldn't the graph be symmetric?
Nice. I hope someone will figure it out. Okay, it's kind of obvious, but good observation. You're. It means that you're following my talk.
So it's just a small question.
Yeah.
This hypergeometric function that you had written, does that fit into this plot?
In some way, yes.
Are these features of the hypergeometric functions?
Not in a direct way. Essentially, the hypergeometric will enter somewhere in the computation of these numbers. This is some function of delta. And they will enter this CS. But it's not very immediate. It's like there's a complicated equation.
Okay. I was wondering whether there's some universality.
I can tell you later about this hypergeometrics, and it's something interesting there as well. But I want to look at this kind of physical picture, nice picture. So indeed, delta equal 1 is the free fermion. When you tune, you see, you get delta 1 when you set lambda to 0. What is lambda to 0? Is setting the Hooft coupling to 0. It's when you're essentially when you turn down the Chern-Simons coupling, essentially down, but you're left with the free fermions in the singlet spectrum, right? Because you still have the Gauss constraint. This is this theory. And does it make sense that the relative anomalous dimension at 1 over n is 0? I guess yes, because you don't have a line essentially. Essentially, there's no line anymore because there's no Wilson line, roughly speaking. And kind of all the operators, whatever their anomalous dimension is, from the bulk, let's say, it's the same. So the relative anomalous must be 0. I mean, at leading order, it's just going to be 1. But then it's going to be 0. It makes sense, kind of. Why is it positive? I don't have an answer for that. I don't know. But you see, interestingly, the higher you go, the smaller it is. It's a kind of, they go down. The values go down. I guess is this something that you could probably explain from CFT arguments, maybe. That the anomalous dimension goes down, the relative anomalous dimension goes down, maybe. Maybe it makes sense when you increase the spin. The relative spin. You see the spin increases. I'm looking at more higher relative anomalous dimension as I go. The values of the anomalous dimension at 1 over n goes down. This is one observation. Now, what happens? So as you turn on the Hooft coupling, okay, it makes sense. You get some anomalous dimension, 1 over n. You can even show some graph. You can probably compute it in perturbation theory. It's probably hell to compute it, but you can probably do it. What happens at the endpoints? So these endpoints are the same, actually. These are when you hit delta equal 3 over 2 or delta equal half. This is what we call the critical boson model. And they're the same point. So why? So first of all, there's some features. So some of them go to 0, which probably makes sense. You probably don't have a line there. But there is this weird thing here at the endpoint on the left, but it doesn't appear here on the right. So first, let's address that. Let's address that. So it's a complicated argument, and it's still under investigation. And this is an informal talk. I'm going to say maybe some very things that are not kind of checked. Okay, it's like a kind of my intuition. It's preliminary results in a sense. I don't know what is going on here. Okay, completely. I don't know completely what's going on here, but bear with me. So.
Sorry, this is numerical.
No. It's analytical.
You can compute CS exactly.
Yeah, I know it exactly. I can do this whole tower exactly. It's hard to do it, so that's why I plot only 3 of those. But in principle, I can do all of this tower. I don't have a closed expression for it. Sadly, it's very hard to obtain it. Maybe in the future, but so what's happening here? Roughly speaking, the reason that you get here 0 and here not is because the spectrum here is shifted by 1. So it measures here at this point, it measures the relative anomalous dimension of this spectrum a bit shifted higher. So roughly speaking, when you see this feature on the left, it's only this that you're looking at. When you sitting here, it's like you're looking at this guy or something like that. So it makes sense why you see it 0. I can make it more precise by literally drawing the spectrum on these 2 points. They're the same spectrum, obviously, but it's just shifted. So when you're looking at this point, you're looking at a spectrum that is shifted by 1 operator above. That's why it's 0 here. Now, I should address why this is, so it makes sense. Like, I want to say it's okay, it can be explained, but this is very hard to explain because, roughly speaking, it means like something distinguishes between the relative dimension of these guys to the whole tower. So naively, what would you expect? Naively, when you sit at the end point, at the special points, you won't expect a line. No line means that all the operators, they're the same, roughly speaking. All these boundary operators, they're the same. You can think of them as coming from the same multiplet, because there's no line, nothing distinguishable between them. So they're like a free scalar, or they're roughly bulk operators. So they sit in the same multiplet of the scalar or whatever, right? So the only thing that can explain this kind of phenomena is the fact that there is a line that you can define in the critical vector model that only affects these operators. It only gives them an anomalous dimension and not for the rest. And there is such a line. It's exactly what we talked about. It's this line. It's the exponent of phi j. Apparently, if you have such an with some coefficient, apparently if you have such an operator, it only gives anomalous dimension to these boundary operators. It doesn't give anomalous to this. And this explains why when we check the relative anomalous dimension between these guys and these guys, we get 0. But between these guys, it gives some kind of special anomalous dimension to it via interactions on the line. But this was not discovered, I think, in the literature, because roughly it's first. I don't know why it wasn't discovered, but moreover, it starts a bit late in perturbation theory, like in 1/n. The coefficient here should be n squared, and alpha is 0.1. I think it's speculation. Okay, I'm giving a speculation, and the idea is that in this endpoint, you have phi dagger phi, and then you're doing perturbation theory, and only these guys get the anomalous dimension, and all the rest, there's no line. So they're like bulk operators in some sense. And whatever they get anomalous dimension from, it's the same for everyone. So the relative anomalous dimension is the same. It's the 0. But specifically for these guys, if you study their anomalous dimension, they get a special correction compared to the rest. That's why we see this there. Why it's not here again is because the spectrum is shifted. So we're looking at relative anomalous dimension of higher operators. So it's again the same argument that they don't see the line. So does that answer your question?
Shifted in terms of delta equal to half spectrum.
In the sense that when you see here the points, it's just this and above, roughly speaking. So it doesn't see this.
But you could do something to track it, to get that curve there. You could look at some other operator. I mean, the full spectrum of operators of lines should be the same here and there.
Yeah.
So
even that, right? I mean, is there any particular reason to believe that?
Parity.
Yeah. You mean the left and the right, or
Lambda
what?
goes to minus lambda and the parity, right?
No, but these are two different theories, right?
No, so take the fermion theory.
Yeah.
Fermion theory at lambda is same as the fermion theory at minus lambda.
Okay.
And you're getting
I see. So without any duality, just
Yeah.
without any duality, these 2 points are
just the same.
Also, the rest of the curves, delta minus 3/2 and higher, they are symmetric. All of those are symmetric, or those are also different?
Symmetric.
Except for the blue one.
Wait. I want to say this is not they're not the same curves. They're smaller.
They are small.
Let me make it more precise. You see, it's not the same curve. Right? It's a different curve. There's no symmetry around this point.
One matches to the other or not?
But only this point is the same point as this one.
No, but then how does that match with parity?
Talking about, so there are two things, Fermi-Bose duality and parity, right?
Again?
The Bose-Fermi duality.
There's no Bose-Fermi duality here.
Okay, so we don't expect any.
I'm agnostic to it.
Okay,
This is the bootstrap method.
okay.
I get what I get. Delta is some parameter. I know that delta equal 1 because I know that the realization is, but roughly speaking, yeah, this should be the free Fermi, and this should be the critical boson, and lambda can run between -1 and 1. But you're saying that this curve should be the same as this curve?
Yeah, sorry, maybe I'm saying something wrong, but I take your calculation, and now I compute. All you're doing is asking how this scales as I increase this, right? So I do this in one frame or a separate parity frame. That takes k to minus k.
You say k to minus k is a symmetry of the theory?
K to minus k is, should keep this. I would have thought the spectrum of how you do this, the scalings that you get by this unchanged. Right? I know parity transformation. It's just same theory reviewed in different coordinates.
Yeah. And
So-
this should flip k?
Yeah, this does flip k, because k flips under parity for Chern-Simons theory. There's no mass in your theory.
But probably this operation also changes the boundary operators or something.
Maybe, but I'm.
But then it makes sense. It just tells you that you're looking at a different
So
anomalous dimension, probably.
That's fine, but if I just look at the full spectrum of all line operators you get, so you may be doing some spectral flow and so on, but if I look at the full spectrum of all line operators, that should go to that.
Maybe half goes to minus half.
Yeah, something like that.
Sure, but then it doesn't mean that for fixed boundary operators it should be.
No, I'm not saying that this should be symmetric.
Okay, yeah.
It should match.
Yeah. This happens.
All the lines.
This happens. If you study now the opposite one or something, you will get the same picture. Yeah. This happens. Yeah. This is for sure consistent. Yeah. Good observation. Yeah. This is true. But here I don't expect to have the same curves on between. I don't expect to have a symmetry between delta goes to 1 minus delta or something like that. All right. I don't expect this to be a mirror.
Sorry, Shiraz, are you saying that there's some different Wilson line on lambda goes to minus lambda, which would give you the same curve, is it?
Yeah, I think so. It seems like it has to be.
Yeah. This is for sure. There is something like that. Yeah. But I want to say there is a prediction here for a new line in a critical vector model that I'm not aware of in the literature. Okay, this is the point of this.
Now, those two are placed at the same point.
Yeah.
So, naively, you might have thought that was a dimension 2 thing to do, right?
A dimension?
You're in the critical boson theory.
No. This is half operators.
They're half operators, but when you take these guys and fuse them.
You mean make them a singlet?
This is not a singlet. Thank you. Got it.
Yeah.
Got it.
Yeah. It's in the adjoint. Yeah. So this is an interesting result. And finally, let me tell you about the 4 points. So the 4 points. Yeah.
Out of your 21 cases, where are you now? So how long are you?
This is the last page. I didn't think it will take that time. So sorry. So the 4 points. So this is the last point. Okay. So everyone, I know you're tired, but I think it's nice to see this result. So I want now to bootstrap this correlation function. I want to determine this. This is some kinematical prefactor times f of chi, where chi is some cross ratio function. How do I do it? Well, very simple. I take this, and I take two of those, and I put here the divergence of J free. From one side, I get the action of charges on M and M. On the other side, I get an integration over MJS prime, MJS prime prime, integrated. I have an equation now, and what's special about this case is that this action of the charge here on this line, it gives it back up to derivatives. So more precisely, this just becomes something like dx2 free squared minus dx3 squared plus dx0 2 free plus dx1 free squared acting on the line. And the right-hand side is roughly speaking the same thing. M32 with some operator here. More precisely, this is just, let me be precise, this is just J0 and this is just J1. There is some derivative here. Oops, sorry. And the point is that, you see, if you can kind of massage the right-hand side to look like something acting with two derivatives on it, with this differential operator on the right-hand side, you can kind of pull out this 4-point. And it can be done for any choice of spins. You see, the input here is this mesonic line that I showed you before. You see, it's just a mesonic line with some bulk operator. A mesonic line with some bulk operator. It looks like a partial wave integral. You know, you have some operator, but here the bulk operator is different, though. And the point is that if you can massage this right-hand side to look something like this with some differential operator acting on each point, you can pull out the 4-point out of it, and that's what we did. We were able to do it. So you see, it's very nice that this charge, there is a specific charge that acts like just a double derivative on the boundary points. And the line, there's nothing about the line here that enters, no integration on the line or anything. Essentially, you just get a PDE with a source term. This is the source. And now I can show you a result of this. Okay, now I'll show you the result, and then you can ask me questions or go eat or something. Let me show you this. So this is the final thing. Let me show you so I'm considering the following correlator. So the superscript is just a choice of the spins of the boundary operators. So this is 3, 2, 1, 0, and I normalize it. So there is no dependence on any normalization. And what I find is the following. I find sinus pi delta squared FEE chi plus F tilde EE chi divided by N pi 3 1 minus delta. So what are these functions, f and f tilde? So f is given by the following differential equation. FEE is chi equal to 1 plus chi G prime EE chi plus 4 minus 2 delta GE chi, and with the boundary condition, with some boundary condition at f equals 0. Let me be not precise about this. And let me give you the integrals. So f e of chi is chi delta minus 1 r squared d free y plus chi e of 3 to the power 5 minus delta y to delta plus 1 and y e3 to delta, and g e is very similar. It's 1 minus 2 delta r squared d free derivative divided by y plus chi e3 5 minus delta y to delta plus 1 y e3 to delta plus 1. Where, let me write you what is chi. Chi is x3, 2, x1, x3, 0, x2, 1. R squared is just y1 squared plus y2 squared, and e3 is just 0, 0, 1. Okay. This is the result. I'll plot you just in a second the plot. But this is the 4-point. So as you can see, it's given by this 3-dimensional integrals, all of them as a function of the cross ratio function, and delta, which is a free parameter, which you can tune between half and 3/2. It interpolates between the free fermion and the critical boson. It actually matches. And yeah, actually, surprisingly, my colleague, a 500 IQ wizard, was able to compute these integrals. This is like a hypergeometric, and this is like a sum of hypergeometrics. You can use there is some hidden Youngian symmetry, if you're familiar with this terminology. And yeah, you can have a bunch of these more complicated functions depending on the spin choices. So the more the higher spin is kind of, or depending on the situation you choose, you can have here hypergeometrics, and then good luck solving it explicitly.
You already knew the expression of each of these operators in terms of the bulk operators.
Yeah. This is an input, yeah.
So one way to proceed, of course, not as explicit as this, would be to just do the OP.
Yeah, yeah, and then you have a sum, yeah. And this should coincide with this one. But then it's not, some of the properties of the 4 points are less clear, right? This way it's a bit more clear. You can study its properties.
But I was thinking that way would also work when the two operators were not aligned.
Yeah.
So you now, in principle, in terms of the sum, have a general expression.
Yeah. But this is, of course, in practical reasons, is more complicated. But yeah, and
interesting for something.
Yeah, that's what I'm thinking for in the future, because you can maybe do two parallel lines, but then you have more cross ratios. That's the problem.
They needn't even be parallel.
Yeah.
It would be like this.
Yeah. And just to give you a plot how it looks like, just for fun. I mean, it schematically looks like so there are various deltas, but roughly speaking, they all look something like this. This is 1. This is not 0 actually. Roughly speaking, so this should be. Let's set this to be 1. Let's say this is 1. This is 0, and this is like yeah. Let's do it like that. They all start at 1. And I use here a parameter zeta, where zeta is 1 over 1 plus chi. So what's happening here? When you're at zeta equals 0, this is the limit where 2 and 1 collide. And the OP expansion between them to leading order gives the identity. And we normalize the identity to give a coefficient of 1. That's why we see 1 here for all of them. But when zeta is equal to 1, this is the limit where one of the lines shrinks. And the leading contribution is just some bulk operator. The false bulk operator is just J1. And it has some OP coefficient in front of it. And the OP coefficient depends on delta. That's what you see them in different position ending in different positions. And now we can do this for various, we can compute this numerically or in some cases explicitly. Or actually only one case we did explicitly. But in principle you can do it if you have enough brain. Okay, that's all. I know it's been a long journey. I'm hoping that you can see from this that it's a nice playground to compute explicitly things, especially for lines. And it seems like lines are a bit somehow easier because people have been doing some stuff with local operators, with 4-point local operators. But somehow here we can do it for any line, any kind of choice of boundary operators. And perhaps these lines are very important in this ADS-CFT because there is this correspondence between Chern-Simons Matter to some quantum gravity theory, which is still a bit shaky. There's one candidate, but it's also been a bit shaky. And the question is also how these lines can be represented in the dictionary of ADS-CFT. This is still an open question. So it could be interesting. Maybe this is a better degree of freedom to work with. Yeah, that's all. So, yeah, thank you. Love to hear questions. I'm here for 2 weeks until the 31. I'd love if you can ask me anything you want. I can give more details and explain better what I did. And that's all. So, yeah, questions?
So maybe in the interest of time, we'll move the questions to last.
Yeah, of course. Thanks.